collapse of 3X in 1997, there was a big mineral laboratory awakening. All the reporting codes like JORC, SANREC, and S43101, they all toughened up their requirements in relation to the use of reference materials. Nowadays, even the stock exchanges require their use. There's a lot of definitions around a control sample, so let's have a look at them. The word standard, it refers to an ISO method or procedure, literally, but it's used to refer to control sample that's now well entrenched. The ISO guides refer to a reference material as opposed to a certified reference material, which is of a higher caliber, has metrological traceability and a detailed certificate of analysis, whereas a reference material, which usually colloquially to encompass all of the different reference materials, may or may not be a certified reference material. So it could be of a lesser caliber. These are internal reference material or matrix matched reference material. I've seen it to mean in-house or internal. They're all custom standards made from the client's own supplied ores, exploration samples, and even metallurgical process concentrates, tails, feed. This term we don't use because I've seen it to use both standard reference material and secondary reference material. The inference that the latter is inferior. So CRMs are used by laboratories to calibrate their analytical equipment, and they use it for their own internal QC, and then geologists use standards as another layer of quality control over what the labs already do. And usually it's inserted at a rate of 1 in 20, but that's dependent on the level of risk, so that ratio could go up. Between lab bias and within lab error, it's all monitored via control charts, and I'll go into that in a bit more detail later. Interlab bias is still a bit of an issue for the industry, but the ISO guides are still working with what to do there, especially when it comes to bankable documents, I believe. So best practice is to submit reference materials in every batch of samples going to the lab, matching the matrix, the concentration levels expected, and the method being monitored. And CRMs are cheap compared to the costs of analytical analysis, the cost of drilling and exploring. So the payback is very cheap. In my 11 years of certifying probably over 1,000 reference materials, I still see a lot of interlab bias. In this example, you can have, you can have 40 ppm at lab A, or you can have up to 46 ppm, depending on the lab. So if you're an explorer, you choose the lab that gave you 46 ppm. But if you're in mine production, you'd be wiser to choose the lab that gives you 40. So QC is done via control charts. In this example, you would plot your certified value as the green line, the center line, and then you can use the SD and the certificate as a first principle guide of what the laboratory may be able to achieve. Otherwise, some manufacturers don't include SDs in their certificates, so they use their own SD as data becomes available. But with this, as you can see, outside 2SD, 4.5% of data will naturally fall outside that. That's 1 in 22 analyses. And 0.3% will fall outside 3SD, as the normal distribution, the bell curve, dictates. And that's 1 in 333. So it's important to remember that naturally things can fall outside without being a problem. So let's look at the rules. Actually, I might just say, so each lab method, as Richard talked about, has its own SD linked to the process. So that may or may not be a good match for the SD quoted in certificates, because that's the combined standard deviation from the analytical program. So the weakness of if using your own empirically derived SD, you don't have any guidance at the start, because you don't have that critical mass of analyses to monitor the precision and bias. So the lab won't be held accountable if you're waiting for it to become that critical mass of data. So this is single rule quality control, and that's simply 2 consecutive results outside 2 standard deviations is deemed a failure. Anything outside 3 standard deviations is deemed a failure. Westgard rules, borrowed from the pathology laboratory, labs, that extends that to look at trend in addition to bias, and the benefits of this is that it reduces the error, the false positives, and at the same time maintaining high error detection. So you look for anything outside 2SD, and then any of these other, there's more rules than this, but I don't have time to go into that. So how do we produce certified reference materials? Well, we dry them at a lower temperature for sulfide-bearing materials to minimise any oxidation, especially for concentrates. We mill 100% minus 30 microns any precious metal content, or if it's an ore that the traces, it's very important for them to be homogeneous, then we'll mill it all to 100% minus 30 microns. Otherwise, the waste rocks, being the greenstone, if we're going to blend that with some gold ore, that can be milled to a finer, so a slightly coarser fraction of 98%, passing 75 microns. We blend the materials, either single ingredient or multiple ingredients, to achieve desired grades, and then they're packaged into single-use units, 10 grams or 60 grams for geologists usually, under nitrogen if it's got more than 2% sulfur, say, as a precaution to prevent oxidation, pyrrhotite especially, it's very reactive. Labs like it in jars. Then representative samples are sent to 10 or more laboratories across the globe with representation from the major and independent lab groups. We try and have geographical representation as well, and use labs that are competent in the type of matrices and concentration that was being sent and the methods being certified. For our RS brand, we can get we obtain collaboration from the lab, so we're able to use up to 40 laboratories. So the types of CRMs are pulp, obviously, and that can be from natural ores or can be made from synthetic materials. Synthetic materials, there's commercially available micronized gold powder, and that can be blended with, I've seen some suppliers use greenstone and, basalt, quartz, and feldspar. It's a good test of the reading process, but doesn't test the robustness of the digestion decomposition step because all the gold is liberated. There's chip standards, and they're good for monitoring the whole process. So the milling, the riffle splitting, they're popular in the bulk commodity industries like iron ore, bauxite, manganese ores. There's blanks and lithogeochem, low-level geochem to anomalous levels. The ore grade standards, you cut off, run a mill, 90th percentile for the high grades. And then there's metallurgical standards. And pigeon pairs, these contain a 1 to 5% offset in the certified values, and they're used to be tricky for a laboratory who may think that there's getting a lot of variability, so if they do any funny business like smoothing data, they'll become unstuck. I'm sure they don't do that, do they? So you submit both standards in each batch at the same time. You should see that offset preserved over multiple submissions when averaged out. You can put the standards in these 32 milliliter cups with a 4 micron polypropylene film for portable XRF. Or we're working on press powder pucks at the moment with a tiny percentage of binder for some of them, and they have the benefit of not having any film, so there's no attenuation of the light signals, and they're good for libs. My father is the managing director of RS Reference Materials. I was speaking with Richard Holdsworth some years ago at a conference, and Richard mentioned, why don't you grab the whole full suite? We've got that in our LIM software, the full OES and MS, and that planted a seed, and I think we spent about $1.3 million on our software now. We're now able to offer super CRMs, which is multiple method specific, full ICP OES and MS scans, where the one single CRM can have up to 180 certified values. So it's a world first. In this example here, you've got 4-acid digest showing all the highlighted elements certified. And these obviously are good for a whole range of applications, including pathfinder elements for greenfields exploration. This is the single most important property of a CRM. Gold being malleable, it's the hardest element to mill effectively and produce a homogeneous product. And there's two types of homogeneity, both relative and absolute. Relative tests like analysis of variance, testing between unit variance, is that bigger than within unit variance? That tests and tells you whether the product is uniform, but it might be uniformly bad because it has high within bottle variance. So absolute homogeneity is the more important factor. So the sources of error you get in analytical data for CRM analyses is any sampling error to the CRM itself, and then errors due to the measurement process. And that can be broken into 3 different types. Within batch variance, repeatability or precision, and as been spoken before, it's important to get the right method at your lab to minimize precision errors. I think once a value gets about 50 times the lower level of detection, it becomes more believable. It rids itself of precision errors as it's isotopically related concentration and precision. Between batch bias, you're sending samples on a different week and you've got a different operator using a different machine, different calibration solutions, so these all contribute to errors. And there's between laboratory biases due to slight differences in the methodology and having different equipment and different operators, different expertise and reagents, etc. So this could be a representation of some gold oil reference material. It's not our reference material, but so you could have a sample that jags nuggets or misses entirely. So this will create a huge sampling error. So a larger sample will obviously be more representative, but is it good enough? That's the question that users need to know when they buy reference materials. How much sampling error are they getting from their CRM? So in this example, the nuggets are destroyed and the sample size is less important. The way to quantify this is to induce a sampling error and then scale that result using the known relationship between standard deviation and sample size to a more practical context, which could be 30 grams for a fire assay. And we do this for every gold CRM we produce. We do it by sending 20 samples for neutron activation analysis with standardized on an 85 milligram aliquot. So that's very small indeed. And we do that at the Australian Nuclear Science and Testing Organisation, government agency in Lucas Heights. And there you can use this formula. This is from Ingemels and Switzer in the 1973 paper. The relationship between standard deviation and sample size. So at 30 grams, this formula here allows us to calculate what the sampling error will be. So we recently did a 10-ton CRM for one of the major laboratory groups to run QC across their global network. The grade's been offset to maintain client confidentiality, but here we sent 20, sorry, it was actually 40 samples. You can see 2 samples in each lot, 85 milligram samples, and this had a 2.9% relative standard deviation. And if that's scaled using Ingemels and Switzer formula, you get 0.15% RSD, and that's what that looks like using the same y-axis. Just tiny 2 ppb level fluctuations. This gives you total confidence that any error you're going to see in assay data is linked to the measurement process, not from the CRM itself. There was a paper published in the Explore newsletter for geochemists by Dr. Nigel Brand, and he procured 4 reference materials at similar grades across 5 different manufacturers and submitted them for neutron activation analysis, 20 1-gram samples at Accolabs Ancaster, and here's the data. As you can see, some producers haven't gotten rid of their micro nuggets. Others have a flatter response. So what could go wrong? So this is a case for not going synthetic. As I mentioned, it doesn't test the robustness of the decomposition step. There was a gold mining company in greenstone terrain. They were using synthetic standards and they switched to using matrix match standards from their own ores, so custom standards. And 2 of them worked really well. And they were happy with that, but 1/3 was giving them troubles, failing all the time. So they stopped using it, discontinued, pulled it from use. And months passed before someone found out that it actually wasn't the CRM at all. It was the type of ore they had. It required a different type of flux for the fire assaying because it wasn't behaving itself. So once they fixed that, they brought the CRM back. This just shows if you don't have total trust in your CRMs, you won't have the confidence to tackle QC issues when they arise. That concludes my speech. Thanks for your attention and good luck with your quality control.